So the whole point of this video lecture actually is to get us started on a new concept, and that concept is energy. And what I want to do is actually take a step back from, I guess, grades and AP and all that kind of stuff and really get a little bit philosophical about what we're doing, because this philosophical approach is in fact going to directly affect all the grades and AP and all that kind of crazy stuff, but it may not seem like it because this discussion is going to be a bit abstract. What I want to do is I want to distinguish two approaches that we've taken to physics, or rather one approach that we've taken to physics from the new one that we're going to try now. So first, I want to kind of review what the forces approach to physics is. And it's really kind of a process that we're going to be, that we've used in our free body diagrams. So we used it in our problems. And we're going to be using it in VPython when we actually do your lab practical later on this quarter. So here's kind of the approach to forces. First, draw free body. So first, actually, you pick a system. Okay. So pick your system, or it's picked for you. So pick your system. Then, of course, what you do is you draw your free body diagram. Using your free body diagram, write down the equations from Newton's second law. And then you solve for constraint forces like tensions and normal forces, things like that. So you solve for constraint forces and your equation of motion. And of course, in beginning physics, all you needed for the equation of motion was like your acceleration. And of course, in AP physics, we're solving for things like the velocity as a function of time, or the position as a function of time. So here's the kind of approach that we're talking about, where we really look deep at causes and see what's going on. So for example, here's our classic box on a table with mass m, and we'll actually, let's just put a force on it. And let's just say the force is 8 newtons and the mass is 2 kilograms. And what I'm going to do is I'm going to really overkill this. I'm sure that most of you just glanced at this and said, oh yeah, the acceleration is 4 meters per second squared, and the normal force is equal to 20 newtons. And I'm sure you did that in your head. But what I want to do is kind of overkill this and kind of show you the approach that we've been taking. I'm not expecting you to learn anything new from this. What I want you to kind of do is look at this and sort of review in your head what has been our approach to physics kind of philosophically. Like, what has been our sort of assumption? And the assumption is that we're reducing everything to specific cause and effect here. So here's my system. I picked it. Now I'm going to go ahead and just draw my free body diagram. And I'm going to do a very good free body diagram where I've got my normal force right here pushing up, and I've got my weight dragging it down, and I've got my applied force. And so I just, picked my system, which was given, and I drew my free body diagram, and now let's write down our equations. So in the x direction, we have F equals capital M times A, and in the y direction, of course, we know that the normal force from the surface pushes up, and that opposes the weight on the object pointing down, and the effect is that those two forces absolutely wipe each other out. So great, we got our, then we can solve for our constraint forces, and of course in AP physics, I would expect you to be able to glance at these equations and just say the acceleration is the force divided by the mass, which ends up being 8 divided by 2, which is 4 meters per second squared, exactly as we said. And of course, when we get the normal force, we get that the normal force equals the mass times the gravity when we rearrange the equation. And of course, we get a normal force equal to 20 newtons when we plug in. So what we've done is we've done this really great approach of looking at every single cause, every single little push or pull, looked at the effect and said, okay, now that we've looked at all these causes, the effect that it produces is an acceleration, blah, blah, blah. And the effect that it produces is a constraint force of, this many newtons. So very, very specific, the word I'm looking for here, and this is a deep word that can get us into a lot of trouble when you talk to philosophers about it, but the approach that we're looking for here is kind of a reductionistic approach to physics. Now, when you all see me tomorrow, we are starting energy. And the problem with energy is that we already have kind of an intuitive idea of what energy is. And, we live in San Francisco, so, we have this kind of intuitive idea of energy like San Francisco, and maybe crystals and healing, and oh, your energy is really nice. And, we have an aura. Here I'll draw an aura. There's an aura, and the little Om symbol. I mean, we had this whole kind of idea of what energy is, and the surprising thing about physics is when you actually look on a deep level at what energy truly is. Like when you say a force, you say, yeah, it's a push or a pull. I get that. It's intuitive. When we really look at what energy actually truly really is, the answer is, especially in beginning physics, it's kind of this thing, in fact, just to kind of illustrate with a bit of a cheesy example, you might as well go with the intuitive example from something like, say, Star Trek.
All systems are going offline, including life support.
Transporter 2, prepare to beam the occupant of the scout ship directly aboard.
Aye, sir.
Mr. Worf.
Mr. Data, lock onto the scout ship, take it in tow.
Energize.
I must see your captain immediately.
We'll get you to sickbay after that.
This cannot wait! I have information vital to your survival.
So that was crazy. I mean, what was that? Energize, and the little glowing thing, and the bad sound effect. But strangely enough, when we actually look at what energy is in physics, we don't define it. We actually don't define it by what it is in some true sense. Like we can say a force is a push or a pull. With energy, we define it by where we can somehow keep it or store it, which is a very strange idea. So you'll hear terms like gravitational energy, and in fact, let me just pick the right color here. So we can talk about things like gravitational energy. I'm going to get a little deeper here. I'm going to call this gravitational potential energy. Actually, no, you know what? We'll call it gravitational energy. And we can talk about kinetic energy. Okay. And we can talk about chemical energy. And really, if you're new to energy, all it looks like I'm doing is I'm taking all these vaguely sciencey words and just sticking the word energy at the end of them. Like gravitational, oh, okay, and energy, and kinetic, and energy, and chemical, and energy. And solar, and energy, and springs, like Hooke's law, spring, and energy. And what other sciencey words can I put energy onto? Electromagnetic, and energy. And all it looks like I'm doing is just listing science words and just stacking the word energy on the end here. But actually what it turns out is that when there is gravity in a system you're studying, or when there is something moving, or you're dealing with chemical energy, like in Mr. Musalam's class if you're in AP Chem, or solar energy like from the sun, or any of these forms of energy, it turns out that there is, and this is going to be the best definition we can come up with, there is this number in the universe that every single type of process seems to have, and we call it energy. So whenever you're dealing with gravity, there's an energy number that goes with gravity. Whenever something's moving, there's an energy number that goes with its moving that we call kinetic energy. Whenever you have a chemical reaction, there's energy that goes into or comes out of the reaction. We talk about some kind of chemical energy. The sun has this mysterious number called energy. A spring that powers, a little toy car, that has energy associated with it. And light, electricity, magnetism, there is some kind of energy number associated with it. And this is the rule that we're going to use that is really abstract, is we are going to find all the ways we can to account for this energy number, whatever this weird thing is, this energy number in a system. And by doing this little trick of accounting for where all the energy goes in a system, we will actually be able to predict. Okay, if we do this, then we will be able to predict useful things And here's what I mean by useful. Things like velocity, displacement, forces acting on the system, spring compression, whether your building is going to fall down or not, whether your bridge will hold. It's really interesting. We have this weird new abstract approach that is absolutely opposed to this forces approach. Totally different forces. We look at all these causes and what happens and why. With energy, we say, well, there's all these different... We're not sure what energy is, but there's this number that seems to just exist in the universe. And it takes on all these different forms: gravitational, kinetic, chemical, solar, spring, and a host of others. And when we look at something, it seems that this number doesn't change in any natural process. Okay? A vague, weird idea. And I want you to sit with that uncomfortable, vague, weird idea, because what we're going to do in class is we're going to do the work of deconstructing that strange and abstract idea.